Hello, today I would like to define three important properties of functions. These are sometimes covered in previous courses, say in college algebra, say in pre-calculus, but they often have different names. So here I'm not sure why the naming often switches at some point, but the injective is the sort of the set theory name for one-to-one, right? Often in college algebra, pre-calculus, calc 1, even you'll see the phrase one-to-one, right? Injective is just another word for one-to-one. So what does that mean? Let's state this in a little more formality. What does injective mean? So here's, if we want to define that, in case maybe you haven't seen the idea of one-to-one, let's define this. So given a function f with domain A and codomain B, we say f is injective, or one-to-one, however you want to call it, right? If and only if for every A1 and every A2 in this set A, right? So for every two inputs that you select in the domain, if A1 is different from A2, then B1 is different from B2. This is the definition of injective. Meaning, if you have A and you have B, and you have different elements, A1 and A2, those are not allowed to go to the same element B, right? This would be not injective, right? Because I have two different elements in the domain going to the same element in the codomain, right? So this would be a failure to be injective. That each element in the domain gets mapped to a different element, to its own special element in the codomain, right? Now, here's something to notice. Notice here, I have a little statement of the form not P implies not Q, right? I have a negation implies a negation. Well, there's a better way to write this. I don't have to leave this definition in this form. We could clean up this definition. Here's a different way to write the definition of injective. We could apply what property from symbolic logic to clean up this definition. If you have not P implies not Q, what's a cleaner way to represent that? What's a logically equivalent statement to not P implies not Q? Famous identity from symbolic logic, contrapositive, right? Reverse the order of the implication and negate both statements, and you get a logically equivalent statement, right? This is Q implies P, right? So there we can apply contrapositive to clean up our definition. So I think the arrow diagram is actually a little more apparent what's going on with the negatives, right? That if A1 is not equal to A2, then when you map them with the function, B1 is not equal to B2, right? Where, and I should specify where B1 is the element that F paired with A1, right? And B2 is the element that F paired with A2, right? So the note in this case, right? What do the B's represent, right? Here I'm taking B1 to mean F of A1, and I'm taking B2 to mean F of A2, right? In this notation. Right? So that's what's nice about the definition with the negations. I think makes the arrow diagram very clear, right? You have A1 and A2 being distinct. So then F of A1 and f of a2, right? These elements b1 and b2, those then are also distinct if a1 and a2 are distinct. But there's another way to say that, which is to say, how do you say it in the contrapositive? You can say that if two outputs are the same, if b1 equals b2, right, then the elements they came from must have been the same. A1 must have equaled A2. That the same outputs could not have come from different inputs. They had to come from the same input, right? So two ways of writing the same definition. Either of these means f is injective. So that's one important property of a function, is the idea of being injective. Now, there's also the idea of being surjective. So surjective is not necessarily always defined in pre-calculus or college algebra. It does also have another name though, just like we sometimes call injective one-to-one. There is another word that sometimes gets used for surjective, which is called onto. And how we define surjective is as follows. So again, we have some function from A to B, right? And suppose the range of f equals the whole codomain, right? Then we say f is surjective, right? Or it maps onto B, right? Meaning it maps onto all of B. It uses all of B, right? So this is some language that you'll see here as far as classifying different functions, right? Now, surjective is maybe a little strange because you can sort of always make a function surjective by just choosing B, the set B, the codomain, to equal the range of f, right? But still, it matters in ways that we'll see soon, right? And we'll do examples of all of these in a bit. So that's surjective. Then we have the idea of bijective. Oh, and I should show the blob diagram for surjective. So what does the arrow diagram look like for surjective? It means that every single element of B always gets mapped to from some element of A, right? That you'll never have an element of B left out in the cold without a dance partner here, right? So another way you could say that if you want to express this in quantifiers, right? You could say for all little b in B, there exists a little a in A such that f of A equals B. Right? This is a perfectly good way to express this idea that the range of f equals B. All right, now bijective. All right, this definition, bijective. What bijective means is both, right? Both one to one and onto. Or you could say bijective means both injective and surjective, whichever language you want to use. So what is how would you define this? To say it a little more formally, right? You could say a function f from A to B is called bijective, or you could use it as a adjective if you want to say it's bijective, or you could say it's called a bijection, right? It's called a bijection, right? If and only if f is both injective and surjective, right? This is the definition of bijective. So, all right. So let's now look at an example, right? Let's consider f to be a function that maps the real numbers to the real numbers. And let's say f is given by the rule f of x equals arctangent of x. So classic function of trigonometry. And I want to look at all of these properties, these three properties, and I want to see which of these properties hold, right? For the idea of injective, surjective, and bijective, right? Let's see what does or what holds or does not hold for arctangent, right? So here, this is a case where we're familiar with a graph here. I can think about this graphically. So I have my x, I have my y, I have these asymptotes, right, at y equals pi over 2, y equals minus pi over 2, and then the graph looks something like this, right? So it's kind of a poor graph, but the essential parts are there. The essential features are there that we need. So here I want to ask, is it injective, right? First, let's ask if it's injective. So the question is, how would I answer if it's injective? Well, if I pick two different inputs, say A1 and A2, do they always, right, where A1 is not equal to A2, do they always get mapped to distinct outputs? Is B1 necessarily distinct from B2, where again, B1 is arctan of A1, B2 is arctan of A2. Are B1 and B2 necessarily distinct just because A1 and A2 are, right? And the answer here is absolutely yes. Yes, if A1 and A2 are distinct, then arctan of A1 is going to be distinct from arctan of A2. Why? Well, a nice way to see this is you could actually see this because arctan is strictly increasing, right? Anytime you go to a new input, the output is automatically bigger than all previous outputs, right? So if your function is always increasing, or vice versa, if it was always decreasing, then automatically you're going to be injective. The function will be injective, right? So that's a perfectly good way to think about this, right? So yes, arctangent is an injective function. And you could say that it's always increasing graphically, or you could say it's always increasing because its derivative is always strictly positive, right? 1 over 1 plus x squared, no matter what x you plug in, you always get a positive number. So it always has positive derivative, right? So there's an example of a injective function. Right? Now, another way to argue that here I used the negated form of the injective definition, right? This one with the negatives in it. I want to also think about it briefly in this form, in the B1 equals B2 implies A1 equals A2 form, the saying if there are, so in the kind of in the contrapositive, right? If the outputs are equal, then the inputs must be equal. So here's another way you could look at this. You could also say that you want to assume arctan of A1 equals arctan of A2, right? Assume those are equal to each other. Then what would I need to prove in order to show that this is injective? Well, we need to show that A1 equals A2. Okay, well, take tangent of both sides. Right, so you get tan of arctan of A1 equals tan of arctan of A2, and then the tans and arctans cancel, and we get A1 equals A2, right? So you can, if you assume that two inputs are equal, you can then prove that the if you assume that two outputs are equal, you can then prove that the corresponding inputs had to be equal, right? So this shows us that that arctangent, sure enough, is injective, right? In two different ways. One, using both the contrapositive form of the definition and the non-contrapositive form of the injective definition. Next, we could ask, is F surjective, right? Is it surjective? Well, to show that it's surjective, we have to show that every possible element of the codomain gets mapped to by something, right? So, no, certainly not. Why is it not surjective? Well, just notice that there's at least one output that never gets used, right? So for example, B equals, let's just pick something bigger than pi over 2 or smaller than minus pi over 2, right? Let's say B equals 2, right? So, you know, if you're up here at y equals 2, right? No input ever gets sent to that output, right? So B equals 2, because 2 is greater than pi over 2, right? So B equals 2 never gets mapped to, right? That is to say, there does not exist an A in the domain such that arctan of A equals 2. Never happens, right? Arctan only maps onto the y values between minus pi over 2 and pi over 2. So this is a function that is not surjective, right? So then you could say, is it bijective? Well, no, right? Because bijective means both injective and surjective, right? So it's not bijective. Because it's not bijective because it's not surjective, right? And it would have had to been both injective and surjective to be bijective. So this is the our function arctangent. Yes, it's injective. No, it's not surjective, and therefore no, it's not bijective. All right. So here now is a very, very, very closely related example that illustrates the kind of strange thing I was saying above regarding surjective being sometimes feeling a bit arbitrary. Suppose you define a very closely related function to the one that we just defined. Keep the domain as all real numbers, but for the codomain, choose the interval, the open interval minus pi over 2 to pi over 2. And again, define the mapping from inputs to outputs via arctan of x. Well, what did I do? I just reduced the codomain from the whole real numbers just to the open interval minus pi over 2 to pi over 2. I modified the function ever so slightly to contrive it to be surjective, right? So this function, this is still injective for the same reason it was before, right? For the same reasoning. But this function with the restricted codomain this is also surjective because every output in the interval minus pi over 2 to pi over 2 gets mapped to by some number, by some real number x. Right? For every b in minus pi over 2 to pi over 2, right, there exists some real number x such that arctan x equals b, right? Again, you can see it on the graph. If you choose any number b between pi over 2 and minus pi over 2, then there will exist, take b out over the graph, there will exist some x that gets mapped to B, right? Because now B can only be chosen between minus pi over 2 and pi over 2, right? And if you want, you could even say what that x is, right? Specifically, what would that x be, right? Well, it would be tangent of B, right? That's what the that's what that x value would be, right? We can even specify exactly what that x value would be. So that's our curious thing that we did here, right? We redefined the codomain to be a smaller set. In particular, we just picked the range of arctangent to be the codomain, right? And now it's surjective, right? Now, because it's surjective, this function f is also a bijection, right? It's bijective, right? And this is a bijection between the sets R and this interval minus pi over 2 to pi over 2, right? So this function f is a bijection between those sets. So it's a little bit, it's just something to be aware of, right? Sometimes, if you say this function f in this example, is it equal or is it not equal to this function f that we defined in this example? Sometimes people say that functions are equal, even if two functions are equal to each other, even if they have different codomains. Or sometimes people would say that the functions are not equal if they have different codomains. So it's a bit just semantics and language and how you want to talk about it, right? There's no objective right or wrong. It's just you want to define equality on your functions to include the possibility where you've redefined the codomain. So, right. So that is an example of arctangent, right? Set up with two different codomains, one in which it is surjective, one in which it is not. In both cases, it's injective, right? In the case where it's not surjective, it's then not bijective. In the case where it is bijective, then where it is surjective, then it is also bijective. All right. Why do we care so much about bijections? Well, there's a big reason why we care. So you can define the inverse function, written f inverse, from B to A is defined by f inverse of B equals A whenever f of A equals B, right? So, and not even just whenever, but if and only if, right? So now it's a theorem that the inverse is a function, right? That this is a valid construction if and only if f is a bijection, right? So this is why this idea of being bijective is so important, because you can define an inverse function if and only if your function is a bijection, right? So what's the picture here? The picture here is that you need each element of A to get mapped to just one element of B by F. So that way you could create F inverse by starting at B and just bringing it back to wherever it came from in A, right? That's how you can build an inverse function. Now, why do we need it to be surjective? Well, it's so that B, the whole set B, it doesn't have domain issues. That's not undefined for some elements of B, right? That you have all of these B's get mapped to by something in A, right? This is why surjective was important. So that way you have something to bring it back to. So this is the theorem that function, right, is invertible if and only if f is a bijective, right? So here, the arctan that was defined on this huge with this huge codomain would not be invertible because the inverse doesn't know what to do with most of its inputs, right? As opposed to this arctangent would be an invertible function because the domain of the inverse would be just minus pi over 2 to pi over 2. And so every input in that set would actually have a corresponding output. All right, so that's why this is of so much consequence, and we'll have more talk about inverse functions in another lesson. So it's almost 10 o'clock, which means campus security is going to come kick me out as they close the building soon. So I will see you next time.